I'd like you to now take a look at some cyclic acetal formations. Now what we're looking at here is a reaction of a ketone with what's called a diol. Now a diol has two OHs in the same molecule. Because the two OHs are in the same molecule, what that means is the compound we end up getting is a cyclic acetal instead of an acetal where there's two different O-alkyl groups hanging off the same C. Now the reason that these are useful is, first of all, they're good protecting groups, and you can read more about protecting groups in your PowerPoint notes. And also they are thermodynamically favored because we're getting a nice stable five-membered ring as a product, and they're kinetically favored because the second OH, when it adds on to C+, is going to be fairly close, so that's going to be a very favorable reaction to have occur. Possibly even more favorable than if you had a second equivalent of alcohol coming in like we have in the non-cyclic acetals. Alright, so let's take a look at the mechanism for this. So we start off with our ketone, and in the first step the H plus adds to the ketone. That leaves a positive charge on the C. Now we can have the diol come in and attack with one of its oxygens, it doesn't matter which. Oops. Alright, so now the diol adds on and we end up with a positive charge on the O that ends up connecting to the C+. So what's happened here is we've used two electrons from this oxygen to form a bond to the C+, and now the oxygen has basically lost an electron to that carbon atom. So now it's positively charged. Now as we talked about before when we were doing these non-cyclic ones, the leaving group is always the one to which a proton will be transferred in any proton transfer step. We know that this OH has to go because if you look at the product, there's no OH present anywhere in this product. So we know that that has to be gotten rid of. And a natural way to do that is to transfer a proton to that. So that's what we're going to do. We're going to transfer the proton from here to this O. And again, look at the pattern of the arrows that I'm using. The O is forming a bond with this H, and then this bond is breaking, and all of that happens simultaneously. Right, that leaves us with the positive charge on this oxygen now. Now we can get rid of that water. That's a leaving group. That's going to leave a positive charge on this C now. And there's the water that left. The water left because we used two electrons from this bond here to add to the oxygen. So now the oxygen got its electron back, but the carbon here lost an electron. That's the carbon that we're talking about, this one here. So it is now positively charged. Now, as I said earlier, this oxygen here is going to be very close to this reaction point, so this is going to be a very favorable process. The O is going to be attracted to that positive charge. And then the O can lose an H plus like that. and that's how we get our product. Now just going back to this step here, this is really the most important step. The reason this O is so close to C plus is just because it's kind of tied into the molecule by the fact that it's the OH is actually part of the same molecule. So you've always got to be on the lookout for things like this, because these are always good situations for reactions to occur. We can force reactions into occurring by putting them close together in space like this.